Hello everyone, welcome back to my channel. I'm Nandini. Today I'm going to discuss about some topics in data science and its applications. So let's get into the video. First is a continuous distributions. Continuous distributions are fundamental statistical concepts that describe the probability of a variable taking on any value within a given range. These distributions provide a way to model and analyze phenomena that can take on the infinite number of possible values such as height, weight, or temperature. The next is a normal distribution. The normal distribution is a fundamental probability distribution in statistics, often referred to as a bell curve due to its symmetric bell-shaped appearance. This distribution is widely used to model a vast array of natural and social phenomena, from heights and weights to test scores and plant growth. The normal distribution is characterized by the two key parameters. They are mean and standard deviation. The mean, which represents the central tendency of a data, and the standard deviation, which captures the spread or variability of the data. This distribution has important properties such as the empirical value, which states that approximately 68% or 95% of the 99.7% of the data falls within 1, 2, and 3 standard deviations, the mean respectively. The central limit theorem. The central limit theorem is a fundamental principle in probability and statistics that describes the behavior of sample means. It states that as the sample size increases, the distribution of the sample mean will approach a normal distribution, regardless of the underlying distribution of the population. This powerful theorem has a far-reaching implications in data science and analytics, as it allows us to make inferences and draw conclusions about the population based on sample data. The central limit theorem is particularly useful when dealing with the complex non-normal data distributions, as it provides a way to approximate the true distribution with a more tractable normal distribution. This simplifies statistical analysis and hypothesis testing, making it a cornerstone of many data-driven decision-making processes. And next, let us see the p-values. In data science, that statistics, the p-value is a fundamental concept that quantifies the statistical significance of a finding or hypothesis. It represents the probability of observing a particular result or a more extreme one, assuming the null hypothesis is true. P-values play a very crucial role in hypothesis testing, allowing researchers to determine the likelihood that an observed effect is due to chance. A low p-value is physically less than the chosen significance level, that is often 0.05, indicates strong evidence against the null hypothesis, suggesting that the observed result is unlikely to have occurred by chance. Conversely, a high p-value implies that the data is consistent with the null hypothesis, and the observed effect may be attributed to random fluctuations. Understanding the interpreting p-values is essential for drawing valid conclusions from data and making informed decisions in the data-driven applications. And next is the confidence intervals. Confidence intervals are the fundamental concept in statistical inference that provide a range of plausible values for an unknown population parameter, such as mean or proportion. These intervals are constructed using sample data and a chosen confidence level, typically 95%, which represents the likelihood that the true parameter value falls within the calculated range. Confidence intervals are crucial for quantifying the uncertainty surrounding our estimates and making informed decisions. By providing a range of values rather than a single point estimate, confidence intervals gives us the better understanding of a precision of our findings and the potential variability in the population. This information is invaluable in data-driven applications where making decisions with appropriate consideration of uncertainty is paramount. Next, let us see the interpreting statistical concepts. Properly interpreting statistical concepts is essential for data scientists to draw meaningful insights and make informed decisions. Understanding the nonsense of measures like p-values and confidence intervals is crucial, as these metrics convey the strength of evidence and level of uncertainty surrounding findings. Careful consideration of underlying assumptions, potential potential bias, and the practical implications of statistical analysis is necessary to avoid misinterpretations or overconfident conclusions. Behind the technical aspects, data scientists must also communicate statistical concepts effectively to stakeholders, translating complex ideas into actionable insights. This requires the ability to explain statistical principles in clear, accessible language, using visualizations and real world examples to enhance understanding. By the mastering the heart of interpretation, data professionals and can also bridge the data and make decision making, empowering organization to make the driven choices. The next is the practical implications, the statistical concepts of continuous distributions, the normal distribution, the central limit theorem, p-values, and confidence intervals as profound practical implications in data science and behind. These tools empower data professionals to make informed, evidence based decisions that drive tangible business outcomes and societal improvements. The first one is the improved decision making. Robust statistical analysis provides a solid foundation for data driven decision making, leading to more effective strategies and better informed choices. Risk mitigation, quantifying uncertainty through confidence intervals and p values helps organizations anticipate and manage potential risks, safeguarding their operations and investments. Enhanced forecasting, applying continuous distribution and the central limit theorem allows us to accurate predictions, empowering organizations to plan and adapt proactively. Let us see some of the advantages and disadvantages. Improved decision making. Continuous distributions, normal distribution, and related statistical concepts provide a robust framework for data driven decision making, leading to more informed and effective choices. Challenges in interpretation. Properly interpreting these statistical concepts requires deep understanding and careful consideration of underlying assumption, potential biases. Risk mitigation. Quantifying uncertainty through p-values and confidence intervals helps organizations anticipate and manage potential safeguarding their operations and investments. Dependency on sample size. The central limit theorem and the reliability of statistical inferences are heavily dependent on the sample size, and which can pose a scenarios with limited data availability. Next, at last, let us see the conclusion. In conclusion, the concepts of continuous distributions like normal distribution, the central limit theorem, p-values, and confidence intervals are fundamental building blocks in the field of data science. These statistical principles enable data professionals to make model complex real-world phenomenon, draw reliable inferences, and quantify the uncertainty surrounding their findings.